In our last lecture, we talked about how close one signal was to another, and we talked about using signal power and signal energy in order to evaluate that. In our next lecture, we're going to talk about how best to approximate one signal by another. But as a preliminary to this, I want to talk about how you can best approximate one vector by another. And I want to do this because you're very familiar with vectors and you're just starting to learn signals. So let's try to start with something you're familiar with to give you some of the mathematics and understanding so that you can move on to the case of signals. So here's our problem. We have two vectors, v and w, shown here. We want to pick a scalar a such that a times w is as close as possible to v. You might want to pause the video for a moment and think about this problem. How should we pick the scalar a so that a times w is as close as possible to v? Now, to answer this question, we first have to decide what best means. Otherwise, we can't possibly figure out how to have a times w be the best match for v. So what do we mean by best? Best in this case means that the error between v and a times w is as small as possible. So we want to make the smallest possible error between v and a times w. So we have to define what that error is, and it's obvious with vectors to define that as the difference, and that's this vector here between aw and v. We'll mark that as e for the error vector. And we're going to measure that error, and the natural way to measure it is to take its length. So that's going to be e dotted with e, and we'll denote that scalar as epsilon. And that epsilon is kind of the energy, if you will, of that vector. It's the length of the vector. So best means the smallest length vector between a times w and v. So how do we find that best value of a? Well, first we'll have to express the error measure, epsilon, in terms of a. So I'll write vector e is v minus a times w. And then I'll find the error. So let's do this bit of vector algebra. I'll write e is equal to v minus a times w dotted with v times a minus w. Let's now multiply that product out, and we'll find it's v dotted with v minus 2a v dotted with w plus a squared w dotted with w. So now that we've found epsilon, we have the question. How can we find the value of a such that we make epsilon as small as possible? You might want to stop the video for a moment and think about this. It's a task of minimizing a scalar by choice of another scalar. Of course, when we want to minimize a function of a scalar by choice of the scalar, all we need to do is take the derivative of the function with respect to the independent variable, the scalar. So we'll take the epsilon dA and we'll set it equal to 0. And of course, that corresponds either to a minimum or a maximum of the function. In this case, it will correspond to a minimum, and we'll call that value a star. So let's take the derivative of epsilon with respect to a, set it equal to 0, and then solve for the value of a star. So the epsilon dA will be equal to minus 2 v dotted with w plus 2a w dotted with w. So solving for the value of a, which makes that true, we find a star is equal to v dotted with w over w dotted with w. That value of a is what we should multiply w by so as to make a times w as close as possible to v. So now that we've found the optimal value of A, I want to ask you a different question. What happens if V dotted with W is equal to 0? So geometrically what that means is that V and W are orthogonal to each other, or if you will, they're at right angles to each other. What will happen in this case? What's the best value of A? Our equation tells us the answer in this case. Obviously, A star will be equal to 0. This result gives us a very useful and new interpretation of the orthogonality condition. Vectors V and W are orthogonal if the best approximation of V by A times W is achieved by setting A equal to 0. This is nice because before, our notion of orthogonality was always purely geometric. It was that the two vectors were at 90 degrees to each other. But now we have a new notion of orthogonality, that V and W are orthogonal if the best approximation of V by A times W is achieved by setting A equal to 0. You can see this idea at the bottom of the page, where I'm showing V and W and the error vector. First for A equals 1, then for A equals 1/2, and then finally for A equals 0. And you can see that for A equals 0, we have the shortest length error vector, E. This notion of orthogonality is going to prove very useful for us in the next lecture, where we'll be examining when signals are orthogonal to each other. For signal orthogonality, we have to break free of geometric ideas. We can't think about one signal being at 90 degrees to another signal.